The first rechargeable lithium-ion battery was commercialized by Sony in 1991 to replace the lead acid that were used in electric vehicles before. As it is nowadays the most used and developed technology for electric mobility, we will focus on it in this presentation. The storage unit in a battery electric vehicle is called a battery pack. This pack is composed of a casing inside of which are assembled a battery management system, also called BMS, that controls the functioning of the cells and the heat regulation system, and battery modules, each composed of a certain number of battery cells connected together in series or in parallel depending on the application. Lithium-ion batteries are composed of two electrodes with different electrochemical potentials, each layered between a current collector on one side and a separator on the other side, all bathed in a saline solution called electrolyte. Such a battery has two separate pathways. One is the separator, that is an insulator for electrons and through which the ion flow. The other is the electric circuit, through which the electron flow, creating a current to satisfy the load. For each electron flowing through the external circuit, a charged ion passes through the electrolyte and travels to the oppositely charged electrode to balance the charge of the system. The positive electrode, called cathode, contains the active materials, the metal oxides. The negative electrode, called anode, is usually made of a layered graphite structure. In the anode, graphene could soon replace graphite as it is the same material but is one atom thick. To prevent short circuits, an insulating layer, named separator, made of plastic polymers coated with ceramic, is placed between the two electrodes. The ceramic makes the cell less sensitive to penetration testing and enables it to operate at higher temperatures. Because lithium is an alkali metal, thus highly reactive to water, a non-aqueous solution has to be used as electrolyte. They are usually composed of conducting salts, organic aprotic solvents, and additives, which contribute to the efficiency and safety of the cells. On these radar diagrams are presented the performances of the most popular lithium-ion technologies used in electric mobility nowadays. NMC, nickel, manganese, and cobalt, is currently the most used chemistry for its high specific energy and good cyclability. NCA, nickel, cobalt, and aluminum, is mainly used by Tesla in their batteries today because they have a good specific energy. LFP, lithium iron phosphate, is the safest lithium-ion technology and is under promising development by manufacturers. LTO, lithium titanate oxide, is an anode crystal compound that can enhance the safety and cyclability of batteries. Let's see next the different shapes of battery and the variety of applications in which they are used. The most important specifications when selecting a battery for an electric vehicle are size, safety, nominal voltage, specific energy in watt-hour per kilogram, specific power in watt per kilogram, and durability, or cycle life. The cycle life of a cell is the number of charge and discharge cycles it can handle before losing 20 to 30% of its original capacity. Battery cells exist in the three following shapes. First, prismatic cells that can reach high capacities and are safer thanks to the pressure relief valve displayed on it, are used in bigger applications such as cars, public transportations, and trucks. Then cylindrical cells that can easily reach high voltages by connecting them with one another in small volume thanks to their small size. They are used in size-sensitive applications such as e-bikes, scooters, or cars. Finally, pouch cells that are lightweight and cost-effective to manufacture are used in certain cars and boats, but there are risks of swelling due to gas generation during cycles. Now let's talk about the electronic components that control the functioning of the modules. The battery management system, or BMS. Regardless of the application, lithium-ion cells need to have a BMS. It's the brain of the cell that controls the heat regulation system and ensures that the battery avoids overcharging or over-discharging that could lead to cell damage. It measures operational parameters such as voltage, current, which is usually measured by Hall effect, and cell temperature during charge and discharge. It is also used to calculate the state of charge, that is the actual percentage of energy left in the battery. Here, we can see two scenarios. The new policies scenario, which illustrates the consequences of announced policies, and the EV30 at 30 scenario, which is the optimistic one, planning to have 30% of electric vehicles in 2030. As we can see from those, electric vehicles are projected to know great expansion in the next 10 years. Should it be supported by the private sector, technological advancement in batteries and electronics, and global engagement towards electric vehicles. By 2026, the price of battery electric vehicles should be lower than that of thermal vehicles. Other businesses, like retrofitting cars, modifying thermal engine cars to make them electric, should develop drastically in the coming years. To facilitate the development of electric vehicles, the grid has to be able to support the high peak powers demanded by quick charges. In order to support this, batteries with reduced capacities coming from electric cars could have a second life there, coupled with renewable energy production to support charging stations. Guidelines for efficient recycling should also be developed to reduce their environmental impacts. It would this way promote circular economy by reusing some of the raw materials from old to new batteries.